We're back. This is the second part of section 3.4. The current rule of signs. The current rule of sign will tell us the number of positive zeros or the number of negative zeros. So let's say we have a polynomial function. Then we say the number of positive zeros will be equal to the number of sign changes. And here's the kicker. Less by an even numbers or less by an even number. Right, we'll talk about that later. But for now, number of negative zeros will be the number of sign changes in f of negative x or less by an even number. So pretty much we just count how many times the sign changes. And then from there we can determine the number of positive zeros and the number of negative zeros, right? Or less by an even number. It is easier to explain by doing a few examples, right? So determine the possible numbers for positive and negative real zeros of that. So good thing here, we just determine the number of zeros here. We're not going to actually find it. We will do that later. Right. Now. So first we'll list the positive, let's say numbers. The number positive zero. Right, I'm just going to rewrite the polynomial. By the way, if this polynomial missing a few terms, it's perfectly fine. Just write the polynomial as is. So even if it's missing a term, like missing x cubed, perfectly fine. Just ignore it. And just count the sign change. So there's nothing changes if we have any missing term. Right, now count. The sign change meaning the sign in the coefficient change from this is plus 1 to minus 1. So this is 1. Minus to plus, that's 2. Plus to minus, well, that's 3. Minus to plus, 4. So 4 sign changes, meaning that the number of positive zeros. So we say there are 4 sign changes. So there are 4 positive zeros. Now, it also says that either that or maybe less than by an even number. So could be 4 or less by an even number, meaning that we're going to subtract 2. In that case, 2 is less than 4 by a 2, an even number. So we subtract 2, then we subtract a 2 until we cannot subtract 2 anymore. If we do that, we're going to have 0. So there are 4, 2, or 0, positive 0. Right. Next we go for the number of negative 0. Right. For that, we're not going to count the sign of f of x. We count the sign change in negative f of negative x. Right, so I put negative x into this. I should write very small here. Negative x to the 4th minus 14 negative x cubed plus 71 negative x squared minus 154 negative x plus 120. Well, that will turn to, I'll continue here. positive x to the fourth positive x cubed positive 71 x squared plus 154x plus 120. Right, what we see here is all of them are positive, so no sign change here. No, so no sign changes. So in this case we say there are no sign changes, so there are no negative 0. There is no negative 0. Of course, if it is 0 less than by an even number, we subtract 2, it's going to be negative, so we're not going to do that. So we stop when we reach 1 or 0. If we stop at 1, we stop at 1 because 1 minus 2 is equal to negative 1, so that doesn't work either. So always subtract by an even number or subtract 2 every time until we have 1 or 0. Right. Now, we can also write a little nice summaries here. So we can say it. It's the positive 0, the negative 0, and imaginary, and then the total. So here's the summaries of the 0. For positive 0, we may have 4, 2, or 0. Negative, we could have none. Remember, this is the fourth degree polynomial. The total must be 4. So if that is the case, there will be no imaginary here, 2 imaginary here, or 4 imaginary here. So those are the only possible scenarios. 4 positive 0, only 2 positive 0 and 2 imaginary, or all imaginary solution. So that help that's what we get from Descartes' rule of sign. Right, let's look at the next one here. First we go with the number positive 0. I'm just going to copy the polynomial. To x to the 5th plus 3x cubed. As you see, we do not have x to the 4th here, which is perfectly fine. We're not dividing them, so we don't need all the terms. Right, let's count. Positive to positive, there's no change there. Positive to negative, well, that's 1. Negative to negative, that's not a change. Negative to positive, that 2. So there are two sign changes. So we say there are 2, because that's 2 sign changes, so there are 2. But remember, less than by an even number, so we subtract 2. If we have 0, we stop. So there are 2 or 0, positive 0. And now we go for the number of negative 0. For that, we'll find the function when x is replaced by negative x. right? So that gives us negative 2x to the fifth, negative 3x cubed, this negative 11, sorry, yeah, negative 11x square, like that, and then plus 9x plus 15. So let's count. That's not a change. That's not a change. This is a change. So there's only one change. So we say there is only one change here, right? And if we have 1, we're not going to subtract 2 because that will give us negative. So whatever the number is, we just keep subtracting 2 until we have 0 or 1. So there is 1, negative 0. Right, and with that we have a summary as follows. Positive, negative, imaginary, and total, right? So for positive we might have 2 or 0, guaranteed to only have 1 negative. The total we have is going to be 5 because that's the 5th degree polynomial. So with that, we guarantee in this problem we have imaginary solution. I'm sorry, this will be 4. Yeah, the total must be 5. So this one must have imaginary solution. All right. Now the next 2 examples, I'm just going to review everything we have in this section or this chapter even. Right, now let's say we have the polynomial. Now we're going to try to find the zeros. Right, so first we list the rational zero, use that rational zero theorem to list all the possible zeros. So possible rational zeros. Have the factors of the last one. The constant over the factors of the leading coefficient 1. Our factor of 16 will be 1, 2, 4, 8, and 16. Factor of 3, 1, or 3. Right? We have 1 over 1, 2 over 1, 4 over 1, 8 over 1, 16 over 1, and then 1 over 3, 2 over 3, 4 over 3, 8 over 3, and 16 over 3. Well, that it is possible, it's not actual. Right, so that divide by 1, and then we divide by 3. 1/3, 2/3, 4/3, 8/3, 16/3. Right, so those are the possible rational zeros. Next, use the remainder theorem to evaluate f of 1 and f of 2 are those 1 and 2 zeros of the polynomial function. So we divide by 1 and 2 into that division. Let's put 1, 3, -4, 12, and -16. Alright, just divide that. So drop down to 3, 1 times 3, 3, that's -1, so that's 11, -5. Since this is not equal to 0, this is not equal to 0. I mean x equal to 1 is not a 0, I should say that. Now try 2, 3, -4, 12, and -16. Right, drop down to 3 again. Give us 6, 2 times 2 is 4, 16, 32, well that's 16. That is not equal to 0, so x equal to 2 is not a 0. So the question is, are 1 and 2 are 0? So the answer is no. And not zeros. Right, so that's it doesn't work. Next, use the intermediate value theorem to show that there is a 0 between 1 and 2. Well, that's easy. 1 is negative, 1 is positive. So there must be a 0 in between them. So we say since f of 1 equal to -5 and f of 2 equal to 16, that means they have the opposite sides, so there is a 0. One positive, one negative. There is at least 1 0 between 1 and 2. Right. Now, if we have to guess which one between 1 and 2, of course we only pick the numbers that is in this list, right? We're not gonna choose any random number. Right, so what number in here is between 1 and 2? Well, not any of those. Not that, not that. Right. 4/3 is 1.33. So out of all the numbers in that list, 4/3 is the actual number. So choose a possible rational 0 in this list, and this is 4/3. So we just choose that and test in this. So a possible number between 1 and 2. So meaning we're going to try 4/3. All right. So 4/3. I'm just going to copy this problem again. 3x to the third power minus 4x squared plus 11x minus 16. So 3, -4, 12, and -16. Write down to number 3, multiply give us 4, subtract 0 times anything is 0, so that is 12, and 12 and 3 cancel out to give us 16, and this is indeed 0. So when it is equal to 0, when the remainder is equal to 0, it is also the values of the function is equal to 0, and that means x equal to 4 over 3 is a 0. Right, we found it. Use the zero factor theorem to factor the polynomial completely. The original polynomial is this. From the coefficient here, we can just rewrite polynomial 3x cubed minus 4x squared plus 12x minus 16 one of the factor is x minus 4 over 3, and then the other factor will have to be what we have here, 3x squared plus 0x plus 12. Right. Yeah. When we do synthetic division, we reduce the degree of the polynomial by 1. Original is a cubic polynomial, now reduced to quadratic. Right. Next, use the Cauchy's rule of sign to determine the number of positive and negative zeros of the quadratic factor of f of x. So this is quadratic factor of f of x. Let's just say q of x for quadratic. X squared plus 12. Now, number of positive zeros. Let's write that again. So there's no sign change, so no positive 0. Try again from negative 0. Right, for that we'll replace negative x into x. Well, there is no sign change as well, so once again there's no negative 0. So that's why we're not going to go back to the list. We're not going to go back to this list and choose any of this number. None of them will work, because we know that the solution is not positive, not negative, and certainly not 0 in this case. So in that case, what we can tell is this one only has imaginary 0. There are 2 of them, right? Imaginary solution come in pairs, and this one has second degree, so there will be 2 zeros. All of them imaginary. Right, so the rest is easy. 3x squared plus 12 equal to 0. I'm not going to even use quadratic formula here. That's easy. Just subtract 12 on both sides. 3x squared equal to 12, negative 12. Divide by 3 on both sides. X squared equal to negative 4. And we take the square root on both sides. Just keep in mind when we do that, there's plus or minus. So we have x equal to plus or minus square root of negative 4, and the negative inside square root, make it imaginary. where 4 is 2. So plus or minus 2i. So what we have here is guaranteed to have no more real solution. So the solution we have 2i, negative 2i, and 4/3. Right. So this example we cover pretty much all the theorem we have in this chapter. There's one more example. Now we're trying to solve for this polynomial and try to find all the zeros. Use the rational zero theorem to list all the possible zeros. Right. So possible rational zero right. So we have the factors of the constant, the last one, and then over factors of the leading coefficient. Right, plus or minus 1, 2, not 3, factor of 20, that is by 4, 5, 10, and 20. Right, and then factor of 3, 1 and 3. Right, now we will use all of those number divided by 1 and then all of those number divided by 3. So plus or minus 1 divided by 1 is 1, 2 divided by 1 is 2, 4 divided by 1 is 1, and then 5, 10, and 20, and then divide by 3, 1 over 3, 2 over 3, 4 over 3, 5 over 3, 10 over 3, 20 over 3. Right. Now use the Cauchy rule to determine the number of positive and negative zero. So number of positive zero right. So we write the function 3x to the 4th, 16x cubed, 17x squared, you might actually have the solution already. No sign change here. All of them are positive, so no sign change. So since there's no sign change, so there is 0 because there's no sign change. Positive 0. So we're not going to try it. If we have to guess a solution from here, we're not going to guess any positive number. So the Cauchy rule of sign allows us to knock out all of the negative zeros. All of the positive zeros, sorry. Now, number of negative 0. Just replace negative x into x for that polynomial. Right. That's going to be positive negative positive 17x squared negative 64x plus 20. So 1, 2, 3 sign changes and 4 sign changes. So we say there are 4. Number or less than by an even number, right? So subtract until we cannot do anymore, meaning when we have 0 or 1. There are 4 positive 0, 2 positive 0, or 0 negative 0. Right. So if we have to guess in this list, we're not going to guess any positive number because that's not going to work. Right, so in that case, we try negative 1. And so synthetic division for negative 1. 3, 16, 17, 64. By the way, synthetic division, if we're missing any term, we have to put in 0 in that. The current rule of sign, we don't put in 0 for missing term. Right, write down 3, negative 1 times 3 is negative 3. And add them 13, negative 13, 4, negative 4, 60, negative 60, negative 40. Right? If the remainder is not equal to 0, the values of the function is not equal to 0, therefore that is not a 0 of the polynomial. What doesn't work? So by the way, in this case we will say they want to evaluate f of negative 1, so we say f of negative 1 equal to negative 40. Right, next. Use intermediate value theorem to show that there is a 0 between negative 1 and 0. Well, we have negative 1. The value of the function is 40. Now, when we put 0 in for x, well, that's easy. If 0 in for x, then that equal to 0, that equal to 0, because x is 0, right? So pretty much that, and with x here is 0, only left with 20. By the way, negative 40 when x equal to negative 1. So f of negative 1 is negative 40, f of 0 is 20, so they have opposite sign. Because they have opposite signs, we say there is a 0 between the 0 and negative 1 and 0. Is at least 1 0, or we should say there is a 0 between negative 1 and 0. Right? Next, of course, we have the whole list here. We're going to pick the number that is actually between negative 1 and 0. Well, between negative 1 and 0, that could be negative 1 over 3 or negative 2 over 3. Let's try negative 1 over 3 first. If it doesn't work, try negative 2 over 3. Right. By the way, if we have a calculator on this problem, we might not even need to do any of this point. Just try to graph it and find the intersection. Let's just do that quickly. 3x to the 4th plus 16x cubed plus 17x squared plus 64x plus 20. Right, and then second, the second 0 equal to y2, calculate And now we find the intersection. There is a 0 there that would look like -5. Actually, -5 may work. Let's see that. We do that. First curve, just hit enter. Right, second curve is that. Now guessing. Just move to the zeros. Hit enter. Well, so that is -1/3. Let's do that again. The first curve is that function. The second curve is the x-axis. Now when we guess, move close to the point and hit enter. So -5 indeed is a 0. Right. But like I said, without a calculator we don't have that. But if we have a calculator, yeah, just try -5, -1/3, and the rest is quadratic. Equation should be simple. Like I said, if we don't have the calculator, we have to do it like this. We review a lot of things. If we have a calculator, we just go ahead and divide by -1/3, divide by -5. Right. So -1/3. 3, 16, 17, 64, and 20. Right, write out the 3, multiply this, -1, that's 15 times -1/3, -5, that is 12. 12 cancel 3 into -4, so that's 60, and -20, and that's 0. So indeed, we have 0 here. Is the values of the function when x equal to -1/3, so -1/3 is a 0. -1/3 is a 0. Right. We know that -5 is a 0, but we're not going to try that. Assume we don't know that. What we're given though is 2i is a 0. So what happens if we are given imaginary? Well, synthetic division also works for imaginary. We haven't tried that yet, but it works. Let's try it. Okay. Of course, we're not going to go with the original one. Every time we find a 0, we reduce the problem to smaller problem. Now we just need to use this. Right. Just the problem now reduce only this. Because that's the zero factor theorem, we don't need the factor of x plus 1/3 anymore. We only need to solve for what's left in the quotient. Right, write out 3 times 2i, 6i. 15 plus 6i is 15 plus 6i. And then multiply. Well, 2i times 15 plus 6i. That's 30i plus 12i squared. I squared is -1, so that is 30i minus 12. The 12 minus 12 cancel out, we just have 30i. Now 2i times 30i it gives us 60 I squared. I squared is -1, so that's just -60. So that certainly works for imaginary as well. Now if this is a 0, then 2i is a 0. Right. The nice thing about this is we can just keep going with the quotient, right? We don't go back to the original. We just keep going with what we have. Now we keep going with this. Now, one theorem we have earlier imaginary solution come in pairs if we have real coefficient. We do have real coefficient. So the negative 2i will also work. So now try negative 2i. Right. So if it works, we just keep going with the quotient. Right. Write out 3. Don't have to go back to the original one. That's negative 6i. Well, 6i and 6i cancel out 15. And multiply this, negative 30i, cancel 0. Once again, this is a 0. So negative 2i is a 0. You just keep dividing like that. And then the next one is easy. The last one, we just have 3x plus 15 equal to 0. Don't need to use synthetic division. Just move 15 and divide by 3. So we have x equal to 5, negative 5, negative 2i, and negative 1 over 3. Negative 2i, and negative 5. That is, of course, if we don't have the calculator. If we have a calculator, we can check. We show that negative 1/3 is the solution. I will do that quickly. If we have a calculator, it shows that negative 1/3 and 5 is the solution. So we go from here. Let's do that again. If we have the calculator, this will be a lot easier. We find that we have the negative 1/3 and 5. So right, and we just keep going with negative 5 because we know that's certainly going to work. Just keep going with this. And the rest, we have 3x squared plus 12 equal to 0. And I think we did one problem like this. We solve for x easily, give us plus or minus 2i. So if we have the calculator, once again, second trace, go to intersection. But before that, we enter the function, and then 0 for the second function, and then second calculate intersection. The first curve is this, so just hit enter. The second curve is equal to 0, yes. And then we just move. When we move closer to this solution, when we hit enter, it will go to that solution. If we want this 0, we move the pointer close to it. Hit enter, it will jump into the actual solution. And once we have those, this is what we do. Just divide by those actual zeros. They should be 0 remainder. Just keep working with what's left, and essentially we have a quadratic equation, which should be simple to solve for. But that's all I want to cover in section 3.4. As always, thank you for watching, and see you in another video in course algebra.